Humans have incomparable advantages in classification tasks, and it has always been a challenging task to integrate human capabilities into the training process of networks. However, the training process of the current deep learning network is still a black box. And it is difficult for people to control the training process of the network. To address the above challenges, we developed an interactive system, SpaceEditing, which has the following benefits. First, it can incorporate human knowledge into the training process of the network, thereby improving the performance of the network. Second, it can guide the learning process of the network, while also helping the network learn features faster and better. Finally, we use it to demonstrate the editability of the latent space, and users can better understand the concept of the latent space during the interactive editing process. Space editing consists of three parts: the function bar on the left, the user workspace in the middle, and the history module on the right. The user workspace is introduced first. It has always been our design philosophy to enable users to visually observe and compare data. We first reduce the features of the data to the two-dimensional user workspace through isomap. The projected data consists of two parts, which are the thumbnail of the data itself and the predicted value of the model. At the same time, the system also has a reminder function. The data with the pink box is the data with the wrong prediction value, which is the focus of the user's movement. In addition, the background of the workspace is presented in the form of a heat map. Using such a spatial layout structure greatly facilitates the interaction between users and data. The main functions of the system are introduced next. Interactive movement is the most basic function of space editing. We provide users with two movement methods, namely single-point movement and multiple-point movement. Users can interact with the data using both methods. Space editing also has zoom and guide functions. When the user hovers the mouse over the projection point, an enlarged view of the data will be displayed, and at the same time, a guide line and a guide circle will be displayed to point out an approximate direction for the user to move. The user can also move according to the heat map of the background. In order to facilitate the observation of the distribution of a certain class of data, space editing provides class display and hide function. Click the sample image on the left function bar to hide or show the corresponding class. Space editing provides two ways to adjust the number of points displayed. The first is to drag the slider at the bottom. The further the slider is moved to the left, the fewer points are displayed, and the more important points are displayed. The further the slider is moved to the right, the more points are displayed. The second way is to control the number of projected points in the workspace by entering numbers in the input box at the bottom right. The manipulated points by the user will be stored in the display box in the history record module, and this function can be used to find the similarities and differences in similar pictures. Clicking a point in the display box can also return the distribution of points in the interface to the corresponding distribution. In addition to the above main functions, the system also has basic moving and zooming functions, as well as redo and undo functions. To synchronize the user's movement in a 2D workspace into a high-dimensional latent space, we design a new loss function. As shown in the figure, we define the point that the user moves as point M, the k points closest to point M before moving are defined as point N, and the k points closest to point M after moving are defined as point P. What the loss function needs to do is to make the distance between M points and P points closer in the high-dimensional latent space, and at the same time make the distance between M points and N points shorter. From this, the network can learn the latent space after the user moves. We conducted experiments on 3 datasets of varying difficulty, and invited 3 different groups of people with different identities to help us with the evaluation. In order to evaluate the results more accurately, we judge from both the visualization results and the performance metrics of the model. The visualization results of the first case study demonstrate that the user's movement can make the visualization result more consistent with the user's knowledge. The visualization results for the second case study show that the visualization keeps getting better after the user moves. The visualization results of the third case study show the impact of 6 users' different mobility strategies on the projection results. In addition to the changes in the visualization results, other performance metrics of the above 3 case studies are also significantly improved, which is enough to prove the effectiveness of our method. In summary, this paper has 3 main contributions. First, we propose a novel and effective method that enables users to interactively edit the latent space based on their own knowledge. Second, we design a new interactive system, SpaceEditing, which can apply our proposed method and allow users to synchronize their operations in 2-dimensional space to high-dimensional space. Finally, we conduct 3 case studies that demonstrate the value of SpaceEditing. Thank you for watching.